start stereoisomerism. And as we have previously stated, these are isomers which arise due to different spatial arrangements of molecules. So stereoisomerism and stereoisomerism are basically divided into two classes: conformational isomers and configurational isomers. Under the conformational isomers, there are some definite standard conformers, that is the fully eclipsed, the gauche you can say. In the original pronunciation it is gauche. The skew, gauche or skewed you can say. Then there is the partially eclipsed, and the staggered. Conformers. And under configurational you have two types: that is the geometrical and another is the optical. The nomenclature of geometrical isomers can be of three types: EZ, sin or anti, and cis or trans. Under optical there are two types of naming: RS and DL, capital D, capital L. So this DL is the relative one and RS absolute. So before going into the conformational isomers or configurational isomers, we have to learn some types of projections used in organic chemistry. We have already seen line angle projection, LAP. Now we will discuss some more projections to represent molecules. So projections. You can have sawhorse projection, you can have Newman projection, Wedge dash, and Fischer projection. For optical activity test, this Fischer projection is very necessary, and also this Wedge dash. So let's go into the details of each type of projections. So let's start with the Newman projection. Newman projection. So in Newman projection, what you do is, suppose this is a molecule and this end has a carbon and this end has a carbon. Suppose the tip of this pen is a carbon and this cap, the back of this cap is a carbon. So what you do is, you have to view either along this tip or you have to view either along this back of the cap. That is, let this be the structure. Suppose this pen represents this molecule. So you have two carbons at the tip, one at the tip and another at the back. So you can view along this side, that is you can view along this, or you can view along this. So if you view, what you do, carbon gone. So the thing is that I have drawn the structure in which when you view along any one of the sides, we represent the front carbon as a dot and the back carbon as a circle. That is, as you see, this one is a dot and the behind one is a circle. So this pen gives a perfect representation in Newman projection of this molecule, that is ethane. So what you do, you can view along this carbon, that is, so you can view along this carbon, or if you view along this carbon, then this should be dot. This carbon is represented by a dot, that is it is called the frontal view, that is you are viewing it from this side and this carbon appears on the front, and behind you see this carbon which we represent as a circle, and we represent the carbon in the front as a dot. So we represent this one as a dot when you view along this side, and we represent this carbon as this circle, sorry, so dot for this one and circle for this one. Then what you do is you simply draw the hydrogens. Now you might wonder that only 3 hydrogens are present. Where are the hydrogens of this backwards? 2 carbons are in eclipsed form, that is, suppose you are viewing along this carbon, this is your front carbon and this is your back carbon, and the bonds are coming out like this from the 3 sides, and also the bonds of the hydrogen of the carbon in the back side So when we are viewing this carbon along the front side, this one is the frontal carbon and this one is the backward carbon. So you cannot see the other 3 hydrogens because these are in eclipse form. That is, the hydrogen bonds present here are fully eclipsing the hydrogen bonds in the backward side, attached to the backward carbon. So you cannot see them. Now if we rotate the backward carbon hydrogen bonds by 60 degree, then you can see them. If you rotate by 60 degree, and why we can rotate this? Because this one is a single bond, and for a single bond, rotation is possible due to overcome of the energy barrier. If you rotate this by 60 degree, then you can see the backward hydrogen. That is, again I draw the structure. This one, and now you can see the backward hydrogen. Okay, so now here 2 carbons are present. If there were carbons, suppose 3 carbons or 4 carbons, then what would we do? So let's take a molecule which has more than 2 carbons. Let's take butane, and now if we see along this side, from this side, then if we view along this side, then what happens is that this one is the frontal carbon and this one is the backside carbon, and to this is C2H5, this whole group is attached, and 1H and 1H, 2 substituent H hydrogens are attached. So how can we represent them? We write this frontal carbon first, that is by a dot, and we represent this back carbon by circle. Sorry, this should be at the center because along the same line, collinear. So this is like this. So we draw the hydrogens for the front carbon. Actually we should not see what the substance of the back carbon. If again this front carbon is eclipsing the back one, but for your understanding, let's write the substituents in the back carbon by placing the bonds a little bit to the side. But as I told you, conceptually, if I write a fully eclipsed form, then the backward bonds attached to the carbon will not be visible. So let's write this one. So there should be two hydrogens and one C2H5 group attached to the backside carbon, and one hydrogen attached to the front also. So I hope you now understand how to represent a multi-carbon molecule by Newman projection. We simply write the front carbon which we are viewing and take the immediate previous one as the backside carbon, and so now I hope that you understand how to draw the Newman projection for a multi-carbon molecule. You just view the carbon along one side, you just view the molecule along one side and number the carbon which you are viewing as the front carbon and draw it with a dot, and draw the immediately previous carbon as the circle, and the carbons which are present and are linked to the backside carbon, you just make them as the substituent of the backside carbon. So here we can write this one as C2H5, which is acting as a substituent now in Newman projection, and also you have two hydrogens. So in this way it is quite easy to convert a line angle projection to a Newman projection. And so let's move on to the Sauer's projection. So guys, we are starting Sauer's projection. So in Sauer's projection, what we do is that we take a view along the perpendicular to the carbon-carbon bond. That is, if this is the molecule, say this is ethane, and this is one carbon and this side is another carbon. So what we do is we place our eye here and we view along this side. So we will see what? That is, we will see a straight line, and that is a straight bond, and one carbon is present here, another is present here, and three spokes which represent the bonds coming out from the carbons on two sides, and which represent, in this case, the bonds attached to the hydrogens. So let's summarize. That is, let's take this ethane molecule, then this is a carbon, we view along this side, so we see the two ends of the bonds containing two carbons and three bonds coming from each carbon. So let's draw it now. So what we view is this one, and this one. Okay, so this is a hydrogen, this is a hydrogen, and for source projection, again, if we draw for multi-carbon species, this is for C2H6, and if we draw for carbon species, then again we have to follow the previous steps as we followed in Newman projection. That is, if we want to draw butane, that is C4H10, then what we will do is this one will be hydrogen, and here it will be 1. If we again break it, then it should be C2H5 and 2 hydrogens. So দেখা যাচ্ছে নিচে এখানে লিখলে, so it should be it should be 2 hydrogens and 2 hydrogen 1 C2H5 for butane. So this is the source projection. And guys, now let's move on to the wedge dash projection. Now let's start wedge dash projection. Wedge dash projection. Now wedge dash projection are of two types, WDP1, that is wedge dash projection 1, and wedge dash projection 2. So WDP1 and WDP2. Let's discuss WDP1 first. WDP1. In WDP1, what happens is that if you view a molecule and you view a single carbon of the molecule, you place two of the groups attached to the carbon. In WDP1, what you do is, when you view a particular carbon of a molecule, you place the carbon along with two of its groups in a single plane. You imagine a plane containing the carbon along with its two groups, and we place the remaining two groups either below the plane or above the plane. So let's take an example. Suppose this is the carbon, and let's take this one. Suppose so let me first draw it, then I will explain. So A, B, C, D. So in WDP1, what we do is that if we view a single carbon of a molecule, we imagine a imaginary plane. We imagine a plane which contains the carbon along with two of its substituent groups, and place the two other groups either below or above the plane. That is, let's take a simple example. Suppose this is the molecule. So this is called a wedge and this is called a dash. And as we have told, we are taking the carbon along two of its groups on an imaginary plane. Suppose this is a plane passing through. This is a 3D molecule. You have to visualize it. Actually, this is sp3 hybridized, so this should be like this. So it should be like so you should have to, you can imagine a plane passing through A, C and B, that is the carbon and its two substituents A and B, and this dash represents that this substituent is present below the plane. That is, if we consider this board to be the plane containing this carbon and the substituents A and B, out of this plane we have this D like this, we have this D like this coming out of the plane, and I cannot show at the back of the board, so you imagine that at the back of the board this this C is going like this. From this carbon, this C is going like this, projecting out from the back of the board like this, the C. So this is a 3D figure. So let's look at this 3D structure. So if you see here, we have told that A, C and B, they are in the same plane, and C means carbon here, and this C and D substituents are out of the plane. That is, if you see, I have denoted this as A. Here let this be C, and let this one be B. So this is making a plane, and in the back we have this dash containing the C group. This is the C substituent, and in the front we have the D, which is represented by this wedge. So I hope you have clearly understood it by this diagram. WDP2, let's write down these notations. That is, wedge represents the group or the substituent coming towards U. That is, if you are viewing, then this D is protruding out of the plane towards U, and by dash we mean by this dash we mean the substituent which is going away from you, that is at the back side of the plane, away at the back. Now let's move on to WDP2. So let's start WDP2. Now what is WDP2? In WDP2 what we do is that we keep two planes towards us and two planes going away from us. That is, if this is the imaginary plane, then we arrange the molecule in such a way that two molecules are coming towards us and two molecules are going away from us. So let this be the A, B, C, D, and we draw the WDP2 for this one. So I Z A, suppose, then we keep two coming towards you, that is these two, suppose, and two below the plane, these two, suppose. So with this we end the discussion on wedge dash projection. Now we will move on to Fischer projection, which is very important for JEE Mains Advanced, especially because of its application in the determination of RS resonance and optical activity, that is mainly in optical isomerism. So thank you guys. Do not forget to like and subscribe our channel, and if you have any query, then please write in the comment box below.